Okay, we're going to get started again, and we're getting to the question and comment period. But I first thought I'd just give a very brief sort of overview of what Claire has presented, if I can. It's a lot of material there. Again, this is geochemical characterization in order to try to predict as well as possible how much acid is going to be produced from waste and tailings materials and how much metals would be released from these. That's a very hard thing to do, to predict that. And she's did a series of, I'd like to point out that even though standard tests are used by most industries, this is not like something that's been tested over and over, and we know the approach, and it's a clear path to how to get to the goal that we're going to. There's a lot of uncertainty involved. I challenged somebody one time with showing me a published peer-reviewed paper that actually has done the standard test and then been able to predict within a reasonable reliability that that's what they got in the field. And I don't think there is such a paper yet, but I think we're getting closer to such a situation. And what the non-standard test doesn't mean that these are any less reliable, doesn't mean they're any less useful. I would consider them myself to be more useful because they are the first attempt to go beyond the simple lab test and try to do a small scaled up field test that gets a little closer to realistic conditions. So she explained static and kinetic tests, the tests that they've done, sort of standard protocols, and she went through some non-standard protocols, which I think were getting us closer to more realistic conditions, and including the barrel test, obviously. And at each time there's another test. She's trying to quantify the release rates, usually in terms of sulfate, but this is also acidity and copper concentrations. Trying to quantify that, again, a very hard thing to do, and compare each kind of test as she goes to more and more tests that are hopefully getting more realistic, including checking against aging of cores, which I don't recall having heard anybody actually done before, which I think is a good idea. You've got cores sitting around at different ages, exposed to air and water over different time periods, and then you can analyze those leachates and see how they compare with the standard tests. Also, subaqueous tests are important because this is one of the ways in which we can keep sulfide materials from oxidizing and creating acid is by keeping them underwater in anoxic conditions. So that's a valuable thing as well. And trying to quantify weathering rates and comparing them is again getting us down that path that we want to be towards, how acid producing is this stuff. And then the goal, of course, is to, once we think we have a good handle on that, figure out what mitigation we need to build into the whole mine plan operation. Okay, and there'll be a chance for more questions on all of this. At this point, we have one of our panel members who's going to give his critique, and I'll let Phil introduce him.
So we'll have... This is the opportunity for the panelists to interact with the consultant who did the work. And we gave our panelists different assignments on different chapters, and also they had the opportunity to put together a presentation or a couple of slides to help direct discussion. And Dr. Tom Al, who we introduced in detail yesterday, is our geochemist on the panel. And he's a professor at the Department of Earth Sciences at the University of New Brunswick, and has worked on geochemical and hydrologic studies of mine tailings and waste rock and the release of constituents to groundwater. So he's going to come up and give a short overview of his critique. We thought it'd be important for Claire to be able to potentially respond while he's going over his critique, so she's at the microphone at the end of the table. And so when he's done, the rest of the panelists will come up and continue the discussion. And after that, it'll be followed by the public discussion period. So, Dr. Tom Al.
Thanks, Phil. Okay, I first want to figure out how things work here. Can I point at all with anything here? Is that it?
Yes, that's it.
Okay, good. Okay, so I'll just go through, as Phil said, a few slides. Claire, at any time, or if you want to jump in and have something to say about what I'm talking about, that's fine. So just first a basic summary of what has been done. Most methods, certainly some of the methods are industry standard, as Kirk said. Others have been modified, showing some tendency towards innovation, and that's all good. Industry standard, I'm not meaning to imply that that's always great and it always gets us to the end that we need to get to. It's, the industry has been evolving over the years and we're getting better, but, there's still lots of things that need to be learned to be able to do a better job. I would say the data are of high quality. They've done a very good job in collecting samples, analyzing samples, compiling data, presenting the data. These data, as Claire mentioned in much more detail, can be used to investigate the potential for low-quality drainage, and that's mostly what I'll focus on, this business of acid drainage. I'm not going to get into too much, copper concentrations, molybdenum concentrations. Claire mentioned the dependence on pH, and that's very important. So if the pH drops, I think we know that the copper concentrations are going to go up. But pH isn't everything, as Claire said as well. Selenium, molybdenum, arsenic, they're not necessarily pH dependent at all. Or not. We don't require low pH in order to see them come from the waste. Okay, so in terms of the work that's been done, it generally falls into this category of prediction, and I guess I want to talk a little bit about prediction and how good we are at prediction as scientists. To do that prediction, there's two basic methods used. Claire talked about static tests, which often are referred to as acid-base accounting. It's, I would say, a useful approach, and here's where standard methods have been employed, and that's all good. It's fairly easy, I would say, to interpret these data when they fall in certain ranges. And I'll show a slide next, and Claire has shown slides similar. When they fall to one end or the other, say into the potentially acid-generating range or the non-acid-generating range, then it becomes pretty clear that we either have a problem or we don't. There's more uncertainty, of course, as you approach this one-to-one line where the acid potential equals the neutralization potential. And there's this often termed the gray zone around that line. So one of the issues is, how do we define that gray zone, that zone of uncertainty? Okay, so what about the Pebble data? Here, what I'm showing is not complete data sets. On the left slide here, the data for the pre-tertiary rock, the mineralized rock, are shown. And the same thing on the right slide, it's the pre-tertiary or mineralized rock from the east zone. So the tertiary rocks are not represented here. And if you recall the data that Claire showed, if, for example, we look at this one, the tertiary rocks would mostly fall in this, hopefully it's showing up as pale green in the upper left. But the pre-tertiary rocks, the mineralized rocks, really fall a few within the uncertain zone defined in blue or in the potentially acid-generating zone. So these mineralized rocks and the waste rock associated with them are essentially acid-generating. And they fall, I would say, far enough within that zone to be confident that there will be acid-generating properties here. Okay, there was work done on the tailings, and here is the presentation of that work. Claire also showed this. I've just put the colors on to help differentiate the different fields. So in these particular analyses, these tailings are what they call low sulfur tailings. The ore has been removed, so a lot of the copper sulfides are taken out, and also they've removed a pyrite concentrate, and that's important to recognize. So So these are low sulfur tailings because a lot of the pyrite's been removed because it's associated with gold, and also the ore or the metal sulfides of interest like chalcopyrite have been removed as well. But still, some of those samples fall within the potentially acid generating range. Okay, so back to prediction. Static tests, or the acid-base accounting, are one way of predicting, but that prediction has no timeline associated with it. So the prediction says, will they or will they not generate acid? And there's nothing about time in that prediction. But when we get to kinetic tests, by definition, kinetic relates to time. So kinetic tests are an attempt to put a time scale on some of these weathering rates, processes, and they use things like humidity cells and aqueous submerged columns, aerated columns, etc., to get some handle on these oxidation rates. So these are done primarily in the lab, but as Claire showed, there's barrel tests that have been done at this site, and at some mine sites they set up test piles and monitor those, and that's all quite useful. But there's some very, very important points to make here. And first off, the lab cannot replicate field conditions, right? So we can take these samples and we can take them into the lab, and we can try to make predictions of sulfide oxidation rates and look at sulfate release rates, and all these parameters of interest are studied. But in the end, we cannot replicate field conditions. So things like complicated drainage flow paths. When you build these waste rock piles, they're notorious. Hydrogeologists trying to understand these waste rock systems are always confounded by this problem. We just don't know where the water's going. Right? It's very, very heterogeneous. There's problems in material mixtures. These piles are not homogeneous in terms of their sulfide content and their neutralization potential and acid potential content. These are very heterogeneous materials just because the mining process goes through different types of materials, and those materials end up on the dumps at different times. Climate variability, okay, seasonal, long-term, all sorts of changes in climate lead to changes in rainfall, temperature, and so on. And all those things add a lot of uncertainty when we try and think about taking the results of these lab tests and as Claire said, scaling up. So scaling is necessary if you're going to use these types of results to understand things like the timing of onset of sulfide oxidation and acidification, or if you're going to try and predict water quality. Okay, again, that type of prediction involves time. We know what the water quality is today, perhaps, but if we want to predict what it's going to be like 5 years from now, 10 years from now, 100 years from now, there's a lot of uncertainty associated with those predictions that involve time. Okay, so I would say it's not possible. I'm making a very emphatic statement here, and Claire might want to refute this, but I'm saying it's not possible to relate lab results to actual behavior of the waste in the field. Okay, that's flat out. I think, personally, that that's a very, very difficult thing, and it's fraught with uncertainty, and we should be very careful if we're going to even go through the exercise of making predictions. We really have to put bounds of uncertainty on that, and it's also a very difficult thing to do. Okay, so here we are. If the aim is to predict the timing of acidic drainage and specifics of water quality, then these kinetic tests, I would say, have very little predictive value. Okay. Now, that has been done. Okay, so, and that's being presented. So this equation was shown earlier, this timing of onset. There's an equation here, and we can talk about the release rate and the effective NP and the critical NPR ratio and so on. All these terms can be defined and can be extracted from, let's say in this case, from the humidity cell test, and they can be put into an equation and we can get a result. But the real issue is, what is our confidence in that result? So confidence in a situation like this comes from repeated successes in prediction. So if we had a record in the mining industry of doing this over and over and over again, and there was success into the, as time goes on, each time, okay, we got it this time, we got it next time, and we get this sequence of prediction and successful matching with prediction from the field results, well, then we would have confidence in this prediction process. But I would say that at this stage, with the state of the art, we don't have that kind of confidence. Okay, we don't have that ability to predict with confidence. So this sort of exercise, we can go through it, but I would say it shouldn't lead us to statements like the one shown here. Okay, so I can't read it very well there, and I can't even see it without my glasses here. So the calculations are consistent for laboratory and field conditions and confirm, very strong language, confirm that the time frame of acid rock drainage generation under site conditions is at least a decade to several decades for fully oxygenated pre-tertiary rock. I think we have to be more cautious in our predictions. I don't think that's the sort of language that we need that's going to take us forward and help us work towards design of site infrastructure and mine planning. So predictions of timing are very uncertain, and they should not be used, I think, for management decisions. Okay, predictions of drainage water quality might be better, and we're talking specifically about drainage water quality, might be better, and I was really glad to see Claire talking about analogs. There's a lot of information on deposits of this type elsewhere in the world, and they weren't necessarily managed as well as they should have been, so perhaps conditions are not as good as we'd like to see at some of those sites, but we can learn from them. We can and should learn from them. And analogs from other mine sites can provide, I think, a lot of information about what drainage water quality might be under specific conditions. So I think that's a great thing to do. And
can I just ask, Steve, my colleague Steve Day actually prepared a sort of draft white paper on exactly that subject, the kind of the data from analogous porphyry deposits and the experiences in other mine sites. And I believe that paper was submitted to the Keystone panel for your review. Have you seen it?
I haven't.
Okay. Well,
No. I'd like to, though.
Yeah. Well, we should make sure that you get to look at that.
Okay, great. Okay, so then just to summarize, we bring the rest of the panel in. From the waste rock point of view, I'd say there's little uncertainty with respect to pre-tertiary waste rock. Under exposed conditions, much of the material, I would say, is likely to generate acid drainage, and I think that's a conclusion that's general, comes from SRK as well. Here's I think one of the most important issues here when we talk about prediction and why we do it and how we use it. Management of waste rock commonly involves segregation of the non-acid generating material from the acid generating material. And for example, that segregation could be required. I have no idea what the plans are here, but it could be required to do something like building tailings dams. So you need rock for constructing these dams. If they could segregate non-acid generating waste rock, use that non-acid generating material to build the tailings dam, that's advantageous. The transport distances, costs are probably lower, and so on. But it's very, very important that it's segregated properly and that the material that's taken out as non-acid generating never does generate acid. So it's very important how these decisions are made for these segregation purposes, and I think we have to be very careful then in getting it right. So this identification is a significant challenge. Particularly, we've seen the pre-tertiary material is dominantly potentially acid generating. The tertiary material, not so much. There's some that is, but not very much by the looks of it. So it seems like it should be fairly easy to get tertiary rock that you could use for construction activities. But issues like using an NPR of 1.6, so that comes from the release rates from the humidity cells, I believe, right?
That's correct,
That's
yes.
where that number comes from. So I think taking that number, it's less than what might be a standard number. So a standard number of 2, 3, sometimes even 4 would be used. I think MEND uses 3. Is it?
MEND uses 3, yes.
Right, right. So to go down to 1.6, I think, based on humidity cell tests, which I don't have a lot of confidence in, seems a little bit risky. Oh, neutralization potential ratio.
That was the NP over AP ratios that I was referring to. I acknowledge that I guess what we need to do is some sensitivity analysis in terms of use of this factor as a decision criteria. I think in general terms, all the pre-tertiary waste is likely to be treated as if it's PAG, irrespective of what that ratio is. It'll probably become a little bit more critical when we're looking at the tertiary material. Now, the majority of that material we believe's NAG, as you call it, but we do know that there's a proportion of it that might be PAG, and I think it's important that we try and differentiate that volume of tertiary material from the rest of the tertiary material and manage it appropriately. And I guess the use of this ratio might not, there are various ways we can use it, and one way would be to try and incorporate it in some way into the mine model, into the geological block model. As I mentioned in my presentation, we've used the total sulfur content in the drilling program as a kind of indicator of sulfide content. We've also explored the use of calcium as an indicator of NP. If we combine those two, we can actually calculate a surrogate NPR value and introduce that into the block model. But we need to define, if you like, a flag value to categorize the material as one type or the other, so that we can have a look at how that material might fall out of the mine schedule and whether it's actually operationally possible to segregate, particular blocks within particular units of material. So, it's a criteria, but how it's going to be used goes beyond just deciding whether it's PAG or non-PAG. It's kind of a tool, if you like.
Yeah.
But yet, you're right, we should certainly do some sensitivity around, changing that value and what implications that might have.
Yeah, the precautionary principle would just say, if 3 or 2 is the number that's used generally, then we need to have good reason to lower it, right?
Yeah,
So,
you're probably right there, yeah.
But I agree with you, if you use calcium analyses and sulfur analyses, for example, in a program that's almost analogous, mining companies segregate materials all the time. That's how grade control operations work, right? You go in and say, well, this is ore and this is waste, and that's done routinely, but it requires a very detailed analytical program and day-to-day kind of being on top of sampling and whatnot. So if you could use calcium and sulfur in a program maybe analogous to grade control, then this sort of segregation, you start to get some confidence in that sort of approach. So, okay, so I think this is my last slide. Tailings, I wanted to make a few comments about tailings. It's actually, there's not really enough information to think about tailings at any great depth. So that's why I say it's a little more complicated. The acid-base accounting results from the low sulfur tailings are close to the zone of uncertainty, but these are just the low sulfur tailings. They don't include that, whatever the pyrite concentrate fraction is. It's not clear to me how much pyrite concentrate there would be, but they have to dispose of that somewhere, and that's not talked about and not really discussed. So if it was co-disposed with these tailings, that's going to push these perhaps out of the range of uncertainty down into the potentially acid-generating range. And so these are the sort of issues that we really don't know enough about because we don't have a mine plan, and we can't really talk about it too much. There's a small number of samples for the same reasons. Okay, so the last point here is really just about the pyrite concentrate. The reason they would generate a pyrite concentrate is so they can recover gold. Gold is intimately associated with the pyrite. So if they concentrate pyrite with flotation techniques, then they can somehow get the gold out of the pyrite. There's several ways of doing that, but none of those are addressed in the EBD, and therefore it's hard to evaluate how those processes could influence the geochemistry of the tailing system. So that's a gap in knowledge at this point. I'm sure it will be closed, but it's not something that we could really address at this point. So, okay, so that's all I have to say. Maybe you want to bring the panel up?
Yeah, I think that's what So at this point, we'll have the full panel up here to ask Claire questions for clarification. And it's the same members as we had yesterday, but we'll just do a brief introduction. On the far left is Dr. Jeremy Richards, Professor of Economic Geology at the University of Alberta. His expertise is he's the economic geologist on the panel and has worked on porphyry and gold systems for a number of years. Tom Al just gave his critique. Dr. Chris Way-Thomas is a research scientist with the USGS here in Anchorage in the Alaska Volcano Observatory, and he is a superficial geologist with expertise in geomorphology, hydrology, quaternary geology, and looks at hazards associated with volcanism in Alaska. Steve McNutt, professor at the University of South Florida, had spent nearly 21 years with the Geophysical Institute in Fairbanks, and his background is in he's a seismologist and working on seismicity associated with volcanoes and volcanic hazards with extensive experience here in Alaska. And then Dr. Larry Goff, who's an emeritus research botanist with the USGS in Reston, Virginia. His expertise in biogeochemistry, soil geochemistry, mineland reclamation, plant ecology. And he formerly was living in Anchorage and has worked for over 30 years in Alaska. So does a panelist have do you want to start with Jeremy? Do you want to work through this? Or I'm not sure how many questions we have here.
Sure, I can kick off.
And we need to make sure we speak into the microphone.
I guess what I would take away from this is that these wastes are going to become acid generating at some point. The equation that you provided for the time of onset, I didn't really understand that equation because it didn't seem that zero was a possible answer. It didn't seem that you could solve that equation for a situation where you never generate acid. It seemed it would tend to infinity, but it appeared that any type of combination ultimately is going to generate acid. So I didn't quite understand that equation. But from what I could see, the materials that are likely to go into the waste rock piles are sooner or later going to be acid generating. And as Tom mentioned, those piles are going to be very heterogeneous. So the likelihood is that for any given pile of waste material, it may start to become acid generating in one part quite early, and then other parts might be later. But I would imagine that acid is going to be generated out of those piles from almost day one. Would that be a reasonable thing to say?
Oh, can I just qualify the like waste rock that's sourced from the pre-tertiary mineralized material? I think we can assume that it's going to go acid at some point in time. Waste rock that's sourced from the tertiary overburden is classed as non-PAG,
Right.
and we wouldn't expect it to go acid.
Mhm.
So, and actually, in terms of the volumes of tonnage to be managed, it's possible that the tertiary might dominate the overall tonnage. So I think that's an important point. Although, until there's a mine plan and a mine schedule, we can't actually put numbers on that.
Right. But I think, from the point of view of thinking about this mine in the long term, it's inevitable that there's going to be acid-generating waste materials produced at some point.
Yes, certainly from that pre-tertiary zone. And the question is, how are those materials going to be managed? Are there containment options, engineering options that can be put into place to ensure that any products of that acid onset are contained or treated before release to the wider environment?
And that would be my question to you, are there?
There are options available. I don't know what options are being considered for this particular site.
But potentially there's an engineering solution to this challenge?
There are potentially solutions. There are ways that you can construct waste rock dumps to try and control and minimise gas transport within the dump. For instance, just to pick one particular control on oxidation rates. I mean, clearly, the oxidation rate for the sulfide to oxidize, it needs access to oxygen. If you sort of imagine a really big waste rock dump. At the time, if you imagined that waste rock dump was constructed instantaneously and was immediately a huge dump, at time zero, oxygen would be available throughout the pore space of that dump. But as that oxygen is consumed in the kind of interior parts of that waste rock dump, it needs to be replaced and before further reaction can take place. And that then becomes a scenario where the whole thing's limited by oxygen supply rates from the external surface of the dump. So you can construct dumps to minimize the permeability of the dump to air transport. And you can also cover dumps with materials that have very low permeabilities. And both those solutions can contribute towards minimizing or controlling oxidation rates.
Okay, thanks.
Claire, I just really have one question here, and it relates to something that was in your presentation. It surprised me a little bit. You talked about subaqueous storage of waste rock, and this kind of relates to what you were just talking about in designing dumps for oxygen transport limitation and so on. Is that a potentially viable option given the volume of material here?
I don't know how viable it might be viable if there was a small volume of particularly reactive waste. Perhaps there's some form of containment where you could envisage there being a permanent pond of water that you could submerge the waste rock within. And if that were possible, certainly submerging the waste rock so that it is covered with water limits the supply of oxygen to that waste material very considerably. Water contains oxygen. Oxygen can be dissolved in water, but the maximum concentration of oxygen in water is much, much lower than the concentration of oxygen in air, which is 20%. So, we're talking about a reduction of orders of magnitude in the oxygen concentration. So those are options, but how viable they are in the context of this project, I don't know the answer to that.
I'd like to actually just remind the panelists that we have a wide range in background in the audience and on the through the web seminar. So let's make sure we keep terminology fairly straightforward, or maybe rephrase things periodically, just so it's clear to as many people as possible. Thanks.
I have a couple of questions too, Claire. Since subaqueous was mentioned here, I'll just remind everybody that this is Alaska, and we have winter usually 6 months, and water quickly turns to ice. So subaqueous storage may be sub-ice storage for most of the year. But this issue of freeze-thaw comes to mind. We have parts of the fall and spring where the temperature hovers around 0 degrees, and freeze-thaw processes are particularly efficient at breaking up sediments. And I just wonder if you guys have entertained the effects of freeze-thaw on how these reactions might be affected, and what could be done about that.
Well, temperature is an important variable in terms of the oxidation rate. And another thing that hasn't been mentioned yet is one of the things that catalyzes or encourages the sulfide to react is the presence of bacteria. And at very, very low temperatures, 0 or close to 0, I think the general feel is that bacteria don't like it very much, and they become dormant or ineffective, and that might actually cause reaction rates to decrease quite considerably. There is some work on in the Divik mine site, I don't know if you're aware of that site, where they have some big test piles of waste rock, and they're actually monitoring the behaviour of that waste rock as a function of freeze-thaw cycles. And some of the data there's quite interesting. Another thing we need to remember is that, and again this hasn't been talked about, it's another level of complexity I guess, is that the sulfide oxidation reaction is exothermic, which basically means it generates heat. So the reaction can actually cause local heating within the waste rock dump, and it might actually in some cases prevent freezing in some scenarios. So the distribution of temperature and the controls of temperature in the heap go beyond the climatic conditions. They actually are also a function of what's going on in terms of the reactions inside that waste rock pile. I'll just say another thing about the kind of logic behind the subaqueous column, as well as generating data that would be pertinent to use of that as an engineering solution for managing waste rock. We were also targeting that at other mine features, like, for instance, if an underground mining method was used and there were underground exposed faces that would, after mining had ceased, would be reflooded, then the subaqueous column data starts to become pertinent in that scenario as well.
Just a couple of other minor questions here. Maybe you could comment on the representativeness of the samples that you used. How realistic are those as what you might expect to actually get out of the mine itself?
That's a difficult question in terms of whether we've covered the broad range of characteristics that are going to be encountered in mining. I would like to believe we have. In terms of whether our sample densities are statistically representative of the volumes of different materials that are going to be mined, I can't really answer that until such time as a mine plan's available and we can actually then compare our sample densities to the actual planned volumes of material that are going to be mined.
So where did you get all that material? Is that from the cores
the
themselves?
The material that we've studied was from exploration cores,
okay.
Mostly diamond drill cores. And basically what we've done is tried to get a good spatial coverage, like both laterally and vertically, but how that spatial coverage actually relates to planned mine volumes, we can't assess at this point in time. I'd like to hope that it's not too far off, but clearly we'll have to refine the data set as we go forward.
The last thing I just want to ask about is just what your perspective is on the long-term acid generation issues, considering longer time scales, like 100, 200, 500 years. Is there some kind of predictability associated with acid generation over time scales like that, or is it completely unknowable?
Well, okay. we are going to try and predict it. But I mean, the point that Tom made earlier about there being uncertainties in this process and the fact that the large-scale waste facilities are complex makes it a very difficult thing to do. But we're going to have a go because you know, you need to start somewhere. But clearly, whatever we predict would be used, if you like, to help form the monitoring regime. And as soon as monitoring data were to be collected that falls outside the bounds of what we've predicted, then we would have to iterate and adapt any predictive model that we'd developed accordingly. So, you know, we've got to start somewhere, and we will try, but there will be significant uncertainties, and what we will try and do is document, you know, where we believe the main uncertainties actually are, and try and do some kind of sensitivity analysis around those. And basically going through that kind of exercise allows you to prioritize data collection as well. So, you know, we'll be doing our best, but, you know, it's difficult.
That's all I have.
I have a question that's looking at some of the basic physics. I mean, one of the parameters as far as exposure and the rates of the various chemical processes would be the surface area that's exposed. So I presume there's some leeway in the design of the shape of the piles and the location to try to structure them in such a way to reduce the rates at which these processes occur.
Well, there's various physical aspects to that question, I guess. I mean, the waste rock pile will include a range of particle sizes from fine material that might be quite similar to the material that was in the laboratory tests to very, very coarse material like huge boulders, for instance. So clearly the particle size of the materials that are in the waste rock dump need to be considered when we're looking at reaction rates. But another aspect is the geometry of the waste rock pile, and that comes back to the point I made before about oxygen supply mechanisms. If you've got a very, very thin, shallow pile that covers a very large surface area, you've kind of maximized the external surface area of that pile. So the behavior of that particular kind of pile would differ from the behavior of a very tall pile, for instance. And all of those questions come back to the mine scheduling and how much tonnage, how much volume of waste is to be managed, and how that waste rock is to be scheduled, and how they plan to construct the waste rock piles. So there are questions related to the shape of the pile that we would have to try and incorporate in our kind of predictive exercise when we get to that stage.
And presumably all these reactions start on the outside of the pile and work their way inward. Is there sort of a core of the pile that never really changes, sort of inert?
Well, that will depend on a number of things. I mean, you also have to think about how quickly the pile is constructed. I mean, you know, usually they're constructed one lift at a time. So certainly before the second lift or the second layer is emplaced onto the lowest layer, then that material is exposed to reaction. But then as more and more subsequent layers are added, the deeper layers might consume the available oxygen and stop reacting and thereafter become inert. But then you also need to remember that if acid water were being generated higher up the pile, that water could then percolate downwards and might leach metals from the lower materials, even though those lower materials themselves are not oxidizing. So there are a number of quite complex processes that we would have to factor into a kind of conceptual model of how the waste rock heap is behaving.
Larry, do you have a...
Maybe this question would be better asked of Craig yesterday when he was giving the soils talk. But in dealing with the reclamation, the mine land reclamation that will you guys will be involved in, certainly. Is there consideration for segregating the sulfide minerals before reclamation, or has that even been considered yet?
You mean like processing the waste rock, if you like?
Yeah, and you know how you're going to be topsoiling and that sort of thing, and planting. I was just wondering if there's a segregation method that you'll be using for these sulfides before the reclamation takes place.
I think there will almost certainly be some form of segregation of reactive materials from non-reactive materials based on some criteria around the sulfide content of the material. In terms of, I think, are you really talking about whether the soil that's kind of scraped off before they mine, is that preserved, and would that be then replaced on top of a waste rock pile?
Right, and of course the depth of that cover soil is critical.
Yeah.
Based upon how much sulfides are in the waste rock that's being reclaimed.
Yes. If you had a heap of very sulfide-rich waste, yes, you'd need to consider if you're covering that with a soil. You're right, it would need to be fairly thick because there is the chance that acid leachates might impact on the health of that soil and impact on the success of any long-term reclamation process. These discussions haven't really yet happened for the Pebble project, so I'm not really sure what options they've got on the table with respect to the long-term reclamation process that they're going through. So I can't really say anything more about that at this time.
Okay. Thank you.
Jeremy, do you have another comment?
Yeah, sure. There's another sort of follow-up. I do feel that there is a gap in the study that's been done so far, and you mentioned it, and that's that no analysis has been done of sulfide-rich tailings. That seems to me to be the most likely problem material. The waste rock piles are going to have pretty low sulfide contents and may generate some acid drainage at some point. But normally the biggest risk from these types of deposits is, as we've been alluding to yesterday as well, the pyrite, which is a waste product, so nobody makes money off of pyrite. As I understand it, some of the ore in this deposit, the pyrite is associated with gold. So the pyrite may initially be treated in the ore stream, but then the gold is going to be separated from that pyrite by some undisclosed process or undescribed process at this point. And ultimately that pyrite is going to be going out into the waste in the tailings somewhere. So as I understand it, the study so far has only looked at sulfide-poor tailings, which are probably not a very significant risk. But if there is a section of the tailings ponds or a separate tailings pond which contains pyrite-rich tails, that would seem to be a very different beast. That's going to need much more attention in dealing with that in the long term. But I don't see that that's really been addressed here at all, that possibility, that apparently inevitable possibility that there is going to be some material like that.
Yeah, I agree that the data set to date doesn't include data that's pertinent to pyrite-rich tails, but those kinds of tailings products have been made available to us recently and have been submitted to the program. So, you know, in the fullness of time, the data from characterizing those materials will become available, and we would incorporate understandings from those data in kind of long-term planning.
So again, I mean, talking into the future, are there examples from other mines where people have successfully contained that type of tailings material effectively in perpetuity, not for 10 years or 100 years, but basically lock that stuff up and it's never going to pose a risk?
There are instances of sulfide-rich tailings in long-term facilities. I mean, actually, tailings in some respects, due to their very fine-grained nature, are in some ways easier to manage than a very coarse-grained heterogeneous waste rock heap, because by its very fine-grained nature, it's much more likely to have a high water content, to be close to saturation, and it's much easier to keep it saturated as opposed to a waste rock dump. And so the geochemical conditions in a tailings facility can generally be managed to minimize oxidation rates. So often in a tailings facility, the actively oxidizing zone within that tailings facility could be quite thin and very near the surface of the tailings. Yes, it's a long-term issue. It has long-term potential, but whether that potential would ever be realized depends on, how that material's managed and what containment strategies are put into place.
Right. I mean, I think that's a critical point. And the concern is that most of the most disastrous spills from mine sites have been tailings dams spills, breaches of tailings dams, leakages, whatever. It's very rarely that waste rock piles cause sort of wide-scale disasters. They might leak a little bit of acid perpetually, but the real risks of a tailings dam spill, is a tailings issue. So it really comes down to the integrity of the tailings dam itself, how it's built, and my understanding, talking to people who build tailings dams these days, is that they essentially design tailings dams to be stable for eternity. You used to talk about building tailings dams, for 20 years or the 100-year storm, but the industry standard now is to build them as though they're going to be there forever. And I think one has to look at it from that point of view, because it's really not good enough to think, it's going to be good for 100 years, but then we're not going to worry about it because people are still going to be living here and salmon are still going to be in the rivers. So I think every time we look at this kind of stuff and talk about time, to me the time really is irrelevant unless you're literally saying this thing's going to be stable forever. If there is some time frame under which it might become acid generating or it might start to leak, then I think a red flag goes up there and you go back to the drawing board to redesign it so that there never is, or at least within the bounds of realistic probability, there never is a chance that it's going to that's going to be a problem. Would that be a fair assessment of engineering practice today?
Yeah, I believe so. I mean, you're kind of taking me outside of my field of expertise here, but there was a bit of discussion of this yesterday, the kind of long-term stability of dams and the ways that different dam walls are constructed and what implications that has to the long-term stability. So some of the discussion yesterday is very pertinent to that point.
Anything else from the panel before we go to the public discussion?